Good day, everyone. Good day, sir. My name is Nicole Joy Imbino, and my topic is about elastic collisions and inelastic collisions in one dimension, 8.4 and 8.5. So I'm going to start at 8.4 elastic collisions in one dimension. So our objectives for today is to describe an elastic collision of two objects in one dimension, define internal kinetic energy, derive an expression for conservation of internal kinetic energy in a one-dimensional collision, and lastly is to determine the final velocities in an elastic collision given masses and initial velocities. So, next is what is an elastic collision? Elastic collision is one that conserves internal kinetic energy. Internal kinetic energy is the sum of the kinetic energies of the objects in the system. So we need to remember that. Now in figure 8.6, an elastic one-dimensional two-object collision is shown here. And the momentum and internal kinetic energy are conserved, which means that in elastic collision, momentum and internal kinetic energy is always conserved. That is what we need to remember in elastic collision. So in here in the figure 8.6, mass 1 pushes forward and mass 2 is facing forward. So there is no collision yet. So that would be P1 plus P2 equals P total. And we need to remember also that in elastic collision, there is no net force, since in the collision here, it is a frictionless surface, so there is no external force or friction exerted. Next, after the collision, the formula would be kinetic energy prime 1 plus kinetic energy prime 2 equals kinetic energy 1 plus kinetic energy 2, since after the collision, there is an internal kinetic energy conserved. So our momentum would be P prime 1 plus P prime 2 equals P total. So as we observed here, the mass 1, the first object, bounces backward, while the mass 2 pushes forward. So in a collision, we would understand where the object would go. Is it either bounce backward or either pushes forward, or it would just stick together? It depends on the collision. So in here, it bounces backward, the first object, and the second object pushes forward. So our equation for conservation of momentum for two objects in a one-dimensional collision is P1 plus P2 equals P prime 1 plus P prime 2, which is there is zero net force, since it is no external friction or force that has been exerted. So if we are going to expound it, momentum is m1 v1 plus m2 v2 equals m1 v prime 1 plus m2 v prime 2. So again, there is no net force. The primes indicate the values after the collision. By definition, an elastic collision conserves internal kinetic energy, and so the sum of kinetic energies before the collision equals the sum after the collision. So we need to remember that internal kinetic energy is the sum before and after, which should be equal. So since kinetic energy's formula is 1/2 mv squared, so it's gonna be 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v prime 1 plus 1/2 m2 v prime 2 squared. That is in two-object elastic collision. This expresses the equation for conservation of internal kinetic energy in a one-dimensional collision. So that's it. So here in example 8.4, we're going to calculate velocities following an elastic collision. So calculate the velocities of two objects following an elastic collision given that our mass 1 equals 0.500 kilogram, our mass 2 is 3.50 kilogram, our velocity 1 is 4 meter per second, our v2, our velocity 2 is 0 since the second object is initially at rest. So we are going to solve that. So now we're going to solve the example 8.4 of the elastic collision. So in the textbook, as you have seen there is no proper computation on where the book get the -3 on in the velocity prime 1. So we're just gonna solve it in a simplified version to understand it thoroughly. So our given again is our mass 1, 0.500 kilogram. Our velocity 1 is 4 meter per second. Our mass 2 is 3.50 kilogram, and our velocity 2 is 0 since the second object is initially at rest. So what we're going to find here is the final velocities of the two objects after the collision. So in order to find that, we're going to use this formula. Our mass 1 v1 plus m2 v2 equals m1 v prime 1 plus m2 v prime 2. So we're going to substitute the given to the formula. Our mass 1 is 0.500, velocity 1 is 4, mass 2 is 3.50, velocity 2 is 0, our mass 1 0.500, and we're going just copy this v prime 1 and v prime 2 since we do not know what is the value yet. So we're just gonna solve that. 0.500 times 4 is 2, 3.50 times 0 is 0, and we're just going to copy this because we do not know the value of the final velocities yet. So what happened here? We're just gonna have 0.500 v prime 1 plus 3.50 v prime 2 equals 2. So next, we're going to solve for the velocity. So we're going to use this formula, v1 plus v prime 1 equals v2 plus v prime 2. And we're going to substitute the given to the formula here. So we're going to have 4 meter per second for the velocity 1, and we're just going to copy the v prime 1 here, and v2 is 0, and we're just going to copy the v prime 2 here. Now, since we are finding the velocity, we're just going to transfer the v prime 1 to the left of the equals. So it's gonna be negative v prime 1 plus v prime 2 equals 4 meter per second. So after that, we were going to multiply this to 0.500, which is our mass 1. So that would be 0.500 v prime 1 plus 0.500 v prime 2 equals 0.500 times 4 is 2, so equals 2. Now we're just going to copy here and here. We're just going to copy that for get the sum. So 0.500 v prime 1 plus 0.500 v prime 1, we're just going to cancel that out because it is 0. And 3.50 plus 0.500, that would be 4 v prime 2, and 2 plus 2 equals 4. So what we're gonna happen is we're gonna divide it with 4. Then you can see that here. V prime 2 would be 4 divided 4 is 1. So 1 meter per second is our velocity prime 2. Now, since we have the v prime 2, we're just going to substitute that. Here, what just we found here, negative v prime 1 plus v prime 2 equals 4. So we're just gonna move the 4 to the right in order to find the v prime 1. So that would be negative 4 since we moved that, plus 1, which is, we recently found that it is v prime 2 equals v prime 1, which is the one we are searching. So that would be negative 4 plus 1 equals negative 3 meter per seconds. That would be our v prime 1. So now we already have the values of the v prime 1, which is negative 3 meter per seconds, and our v prime 2, which is 1 meter per seconds. Now all we're going to do is to check if our computation is right, since we use the simplified version of that formula. Now we will going to substitute our calculation, or the given and our calculation, to the formula. So our mass 1 is 0.500 kilogram, our V1 is 4 meter per second, plus our M2 is 3.50 kilogram, our velocity 2 is 0, equals M1, again 0.500 kilogram. Our velocity prime 1 is negative 3 meter per second, plus our M2 3.50 kilogram, and our velocity prime 2 is 1 meter per second that we just recently found. So that would be 0.500 times 4 is 2, 3.50 times 0 is 0, so that would be 2 plus 0 is 2. And then 0.500 times negative 3 is negative 1.5. Then 3.50 times 1 is 3.50. So that would negative 1.5 plus 350 equals to 2. So it has been said that the before collision should be equal to the after collision. Then we know that our calculation is correct. Okay, now that we have the final velocities of the two objects, which is the first object negative 3 meter per second, and the second object is 1 meter per second. So what does this mean? This means that the negative 3, which is the first object, bounces backward because based on its size, it's only 0.500 kilogram compared to the larger object, which is 3.50 kilogram. So the 3.50 kilogram pushes forward, but only a little. It is only 1 meter per second because the second object is larger than the first object. So that would be all for the elastic collision.